All right, let's just jump right in. We're about to talk about one of the most clever, most powerful, and, let's be honest, kind of weird ideas in all of engineering. We're talking about the imaginary trick that makes our very real electronics actually work.
I mean, it sounds like a total contradiction, doesn't it? The electricity coming out of your wall socket, that's about as real as it gets. So why on earth would engineers, the most practical, down-to-earth people you can imagine, use the square root of -1, an imaginary number, to figure it out? That's the big mystery we're going to solve today.
And here it is, our first major clue. This quote comes from a chat between physicists and engineers, and it tells us the whole secret. This supposedly complex method, it's not about making things harder. It's about making things way, way easier. It's a secret weapon for taming a really nasty mathematical problem.
So what is this problem, this mathematical beast? Well, before we can appreciate the solution, we have to really understand the challenge that engineers were staring down.
Okay, so the power that runs pretty much everything is alternating current, or AC. It doesn't just flow one way, right? It wiggles back and forth, over and over, in this nice, smooth sine wave. Now that's fantastic for sending power over long distances, but for the people actually designing the circuits, that constant wiggling creates a massive headache.
And here's that headache in all its glory. You see this thing? This monster equation? You'd think this is for, I don't know, a spaceship. Nope. This is the math you need to solve for a simple circuit. Just a resistor, an inductor, and a capacitor. To figure out what's happening in that basic setup, you have to solve this, a second-order differential equation.
And trying to fight this thing head-on? That's called time domain analysis. And trust me, it is every bit as painful as it looks. It's a total slog of trigonometric identities, messy calculus. It's just clumsy. There had to be a better way.
And of course, there was. A shortcut so brilliant, it honestly feels like a magic trick. Instead of wrestling with that complicated wave, engineers found a way to step sideways into a different mathematical world where the problem becomes almost laughably simple.
And this is the magic key that unlocks the whole thing. It's called Euler's identity, often called the most beautiful equation in all of math. And what it does is show this unbelievable connection between the number E and the sine and cosine waves we use for electricity. And that little j you see? That's what engineers use for the imaginary number, the square root of -1.
So what does this equation let us do? Well, it lets us stop thinking about our clunky, awkward sine wave, and instead imagine it as just the shadow of something much, much simpler. A little arrow, just spinning around in a perfect circle. And believe me, the math of a simple rotation is way easier than the math of a wave.
So here's the hack. This is the core of the whole idea. You pretend, just for a moment, that your real-world sine wave is this imaginary spinning arrow. Then you do all the hard circuit math on that simple rotation, and when you're all done, you just look at its shadow. You take the real part of your answer and, poof, out pops the correct real-world solution. It's amazing. Now this move isn't just a clever trick. It's a whole new way of seeing the world. It's like putting on a new pair of glasses. We've just entered what engineers call the frequency domain. And this just lays it all out perfectly. On the left, in the old time domain, you're stuck slogging through calculus. Every derivative is a whole thing. But on the right, in our new frequency domain, calculus just vanishes. The hard operation of a derivative becomes simple multiplication. We've literally traded a hard calculus problem for an easy algebra problem. And in this new world, we get these cool new tools. Things like capacitors and inductors get a new property called impedance. You can basically think of it as AC resistance. It just tells you how much that part is going to fight back against a wiggling current at a certain frequency. All of a sudden, these tricky components start acting like simple resistors.
And our signals get a new name too, phasors. A phasor is just a complex number, but what it does is it wraps up a wave's two most important features: how big it is, its amplitude, and its timing, its phase, all into one neat, tidy package. It's basically a snapshot of that spinning arrow we saw a minute ago.
So, okay, we swapped calculus for algebra. We swapped waves for these little snapshots called phasors. What's the big deal? What's the actual payoff for all this mental gymnastics?
This is the payoff. Look at this. On the left, that's the answer you get the hard way with time domain calculus. It's a jumbled mess of sines and cosines. On the right, that's the answer you get using phasors in the frequency domain. It's clean, it's simple algebra. They both give you the exact same answer,
But come on, which one would you rather work with?
Oh, and it gets even better. Because phasors are basically just arrows, we can actually draw them. This is a phasor diagram, and it lets us turn all that complicated electrical math into simple, intuitive pictures. You can literally see the relationships between voltages and currents just by looking at the drawing.
And look, this is not just some neat party trick for electrical engineering students. This imaginary shortcut is the absolute foundation of our modern world. It's essential for designing the power grids that light up our homes, for making the audio filters in your headphones work, for building every radio, every cell phone, every Wi-Fi router that connects us.
So the big idea to take away from all this goes way beyond circuits. It's that sometimes the best way to solve a really tough, real-world problem isn't to just charge straight at it. Sometimes the smartest path is to take a little detour through an imaginary world.
And that really just leaves us with one last question to think about. This was all about solving an engineering problem by jumping from one perspective to another, from time to frequency. It just makes you wonder, what other problems are out there waiting for us to solve them if we can just find the right imaginary world to take a detour through? Where else can changing our perspective change everything?